this is Dr. Ochoa. This video is going to help you draw organic molecules correctly. So when we're trying to draw organic molecules, and we learn this in general chemistry, usually we look at obeying the octet rule and adding up the valence electrons based on a formula. But what happens is when the molecules get very large, that starts to become less practical. So the way I like to teach students to draw organic molecules correctly quickly is by using their periodic table sort of as a cheat sheet. So you want to focus on two things. The first is, of course, the octet rule. So carbon, nitrogen, oxygen, fluorine, all the group 7 elements should have an octet. Okay, and in this periodic table here, all the colored elements are the ones we're going to see the most in organic chemistry. The second thing that I tell students to do is to know what each element looks like in a molecule when it has zero formal charge. So we're going to focus on those two things, octet rule and formal charge. And here's a quick way to remember when the elements carbon, nitrogen, oxygen, and the halogens have a formal charge of 0. So if you go right above carbon, I'm going to make a little chart for the number of bonds and the number of lone pairs. Okay, actually let me move that over. Okay, so the group number for carbon is 4, right? The same as the valence electrons. Carbon wants to have 4 bonds, 0 lone pairs. Okay, then start counting down from carbon. 4, 3, 2, and 1. Okay? Because each bond gives you 2 electrons, carbon will be satisfied when it has 4 bonds. But nitrogen won't. It only has 6 electrons with the 3 bonds, so then it should have 1 lone pair. Oxygen, 2 lone pairs. The halogens, 3 lone pairs. So if you remember carbon 4, right, and then count down 4, 3, 2, 1 on your periodic table, and then 0 lone pairs for carbon, and then 1, 2, 3. Moving on, that's a quick way to remember what those atoms look like in molecules when they have 0 formal charge. Okay, so let's start with CH4. We usually start with CH4, it's a good example. So normally we draw our line bond structures or Lewis dot structures by adding up the number of valence electrons, which is for each element the same as the group number. So carbon 4, each hydrogen 1, so 4 total, so that's 8. Now carbon, to have an octet, is going to have all 8 of those electrons around it. Okay, hydrogen doesn't have an octet, it has a duet. And 1 bond to hydrogen is enough to satisfy that. Now, if I don't count the number of valence electrons, and I just remember carbon, formal charge of 0 when it has 4 bonds, and I bond it to each one of the hydrogens, I'll end up with the same exact thing. Now notice here I'm not focusing on the geometry, just drawing correct line bond structures. Some things to remember, each bond, 2 electrons, each lone pair, 2 electrons. So then we move on to ammonia, right, NH3. Nitrogen group 5, hydrogen group 1, so we have 8 valence electrons. Nitrogen is going to need all of those valence electrons, all of those 8 electrons to satisfy its octet. And if we remember from our chart, nitrogen, 3 and 1, 3 bonds, 1 lone pair. So that's really what I want you to remember. Carbon 4 bonds, nitrogen 3 bonds, and 1 lone pair. Okay, I didn't actually need to add up the number of valence electrons. I could just have started by looking at these and saying this is a neutral molecule. This molecule only has non-metals. Right? It doesn't have lithium, it doesn't have sodium, it's just nitrogen and hydrogen, 2 nonmetals. So I'm only going to form covalent bonds. Neutral, or only covalent bonds, I'm going to use my cheat sheet. 3 bonds and a lone pair. Now if we move on to slightly larger molecules, right, given the formula, for example, C3H8, I'm going to continue to add up the number of valence electrons, and then after a couple of examples, I'm just going to stop doing that. So here you're given the formula, you add up the number of valence electrons, should add up to 20, right? 3 times 4 plus 8, so you get 20. I'm not going to try and draw a Lewis dot structure, right, in which you start going like this. Right, I'm not going to do that. That takes too long. I'm going to take one carbon, give it 4 bonds. Okay, then I'm going to take a second carbon and then a third carbon. Each one of those, I'm going to give it enough bonds to reach an octet. Why did I do 3 carbons? Because that's what the formula is. Then I'm going to use the hydrogens to satisfy the formula and to bind to the carbons. And so this is very common. It's a hydrocarbon. It's just those two nonmetals, carbon and hydrogen. I bonded each of the carbons to each other, and then I finished up the octet by using the hydrogens, right? Drawing bonds to those carbons, between those carbons and those hydrogens. So here you're given the formula. You could also be given this molecule as a condensed structure in which it would look like this: CH3, CH2, CH3. That's what we call a condensed structure. Okay, so if you look at the condensed structure, it tells you this carbon is bonded to 3 hydrogens. That's what I did. To satisfy its octet, it has to be bonded to the next carbon. That's what I did. That second carbon is bonded to 2 hydrogens, and then it's also bonded to the third carbon to satisfy its octet. And then the third carbon has 3 hydrogens on it. So when you're given the condensed structure, it lowers the number of possibilities for isomers to draw. Now, because this formula is only C3H8, there's only one molecule you can draw. But what if the formulas get larger? Notice actually, before I move on, I didn't even count the number of electrons. I know that because I satisfy the octet of every carbon, and I use C3H8, it has to add up to 20, okay? If I had not drawn each carbon with 4 bonds, then there would have been room for a mistake here. But it has to be 20 electrons because each carbon has an octet, and I've used every atom in the formula. So let's say we have C5H12. Okay, that's the formula. There's a couple of isomers with that formula. I can start just by taking taking all 5 carbons and making a chain. 1, 2, 3, 4, 5, and drawing enough bonds, okay, to satisfy the octet. Because this is a saturated hydrocarbon or an alkane, I have enough hydrogens to satisfy, or to have 4 single bonds on each carbon. And you can count them: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I know it's just going to be single bonds all around. That's one possible isomer with this formula. It's correct because all the carbons have an octet, but it's not the only one. There are quite a few. For example, I could have made a chain that was 4 carbons long, and then put a branch on, for example, this carbon, the second carbon. In that case, I'm going to then go back to having an octet by putting 4 bonds on each carbon. H, H, and H. I know my H's start to look like a +1 a little bit there. Let's see. Again, I don't even need to count the electrons. I know that I have the correct number of valence electrons, 5 times 4 and then 12. I know they have to be right because all of my carbons have 4 bonds and 0 formal charge. And I'll remind you how to calculate formal charge, but I want you to train yourself to always start carbon 4 bonds, 0 formal charge. If we start to see ionic compounds, then we have to worry about formal charges. But when we only have non-metals, right, carbon and hydrogen, for example, no formal charge. When we have non-metals, no ionic bonds. So if I wanted to write the condensed formula for this isomer at the top, the linear isomer, it'd be CH3, right, for this first methyl, CH2, 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 CH3. So there's the condensed formula. If I wanted to write the condensed formula for the isomer at the bottom, starting from left to right, CH3, CH2, then I have a CH, here's a CH. On that carbon, there are 2 methyls, so I can put them in parentheses and put a 2 on the outside, because that carbon, which is this carbon here, is bonded to a hydrogen and 2 methyls. So there's the condensed structure. So you might also want to practice going the other way, going from the condensed structure to the full structure. Okay, so let's get slightly more complicated. So still using carbon and hydrogen, right? So just non-metals, so only covalent bonds. But now our formula is for an unsaturated hydrocarbon. So there are not enough hydrogens in the formula to have single bonds. You could go back and count the number of valence electrons. 3 times 4 plus 6, so that gives you 18. But always remember, the goal here, because it's a neutral molecule, is to get an octet on carbon with 0 formal charge. So I start to make a chain, and maybe I start the same way as I did before, right? 3 carbons in a line, and then putting enough bonds on the carbons to get an octet. Right, so obviously this isn't going to be right because I don't have that many hydrogens. 1, 2, 3, 4, 5, 6, 7, 8. I only have 6. So what do? I'm going to erase 2. So now I'm down to 6. Then I'm going to move 1 to this carbon. Okay, well now my carbons don't have an octet satisfied. Okay, if you count the electrons right now, you'll see that there's only 16. 2, 4, 6, 8, 10, 12, 14, 16. The way to satisfy the octet of those 2 carbons is by using a double bond. So if you look at the formula for the hydrocarbon, it is C3H6 or CnH2n. That is the formula for an alkene, so there has to be 1 double bond. For the alkanes, it was CnH2n plus 2. So then we would have had no double bonds. The condensed formula for this, from left to right, CH3, CH, for this carbon here, CH2. Okay, so when I read this from left to right, this carbon is bonded to 3 hydrogens, and then the second carbon. And that carbon is bonded to 1 hydrogen, and then it has to be doubly bonded to this carbon. There's no other way for the carbon in the middle to get an octet. Now let's say instead of having just carbon and hydrogen in the formula, we have a halogen. So C3H5Cl. So halogens really just take up the place of 1 hydrogen on carbon. So you can add up the number of valence electrons, 3 times 4 plus 5 plus 7, right, group 7 for the halogens. That gives you 24. If you just want to double check. If you don't do this, you can still get the correct molecule. And we're going to start just drawing a linear chain here. There are multiple isomers, but I'm just drawing 1 here that's correct. So maybe I started like this again. And I said, okay, H, 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 H. Okay, Okay, and I know I had to put the chlorine somewhere. Oh, too many hydrogens, right? Because this is equivalent to C3H6. The chlorine is just like taking the place of a hydrogen when we talk about the double bond equivalence. Okay, so I'm just going to erase the extras. Okay, I erase one from this carbon and one from this carbon, and then give it a double bond. Now that's not correct geometry, so if I want to fix this a little bit more, make that trigonoplanar there. Okay, so I've used the correct number of hydrogens. I've used 5, chlorine, and I had to include that double bond. I just chose to put the double bond in the chlorine on the left. If I put it on the between this carbon and this carbon, it would have been the same isomer. Now, if you count the number of electrons right now, you don't have 24 because I didn't include the 3 lone pairs on the chlorine. But now you have 24. There's another isomer here. Okay, so try to draw the other isomer on your own. Okay, so it gets a little bit more complicated, but the same approach. The octet rule must be obeyed. There are no formal charges here, so each carbon should just have 4 bonds. Okay, the condensed structure for this is to be complete CH, Cl, right, so that's my carbon here, CH, carbon in the middle, CH3. There's my condensed structure. Okay, so let me give you a condensed structure and then start from there. And I'm going to put a nitrogen in it now. So I don't have any metals in here. I don't have any polyatomic ions. This is a covalent. This is a molecule only with covalent bonds. I can start from left to right to draw a correct line bond structure. Because this is condensed, you should only draw one molecule. You're not given the formula, you're just given the condensed structure. So carbon on the left has 3 hydrogens bonded to it. And then to complete its octet, it's bonded to a nitrogen. Wait, wasn't there something I was supposed to remember about nitrogen? Oh yes, nitrogen, 3 bonds, 1 lone pair. Okay, there's a lone pair, 1 bond to the methyl here, 1 bond is going to be to this hydrogen. The 3rd bond is going to be to this carbon here. Okay, and then I'm going to move on to that carbon and say it has 2 hydrogens bonded to it. And then the next carbon, zero formal charges on the nitrogen because I have 3 bonds in a lone pair. Okay, so let's get again a little bit more complicated. So what if I had CH3, NH, CH, CH2? Okay, so I can start carbon on the left, satisfy its octet with 4 bonds. The 4th bond is to that nitrogen in the formula, the condensed formula. Nitrogen, 3 bonds in a lone pair. 1 bond to a hydrogen, and then 1 bond to this carbon. That carbon only has 1 hydrogen on it. So right now it just has 2 bonds. So I know it needs to be double bonded to the following carbon. Right? There's no other way for it to obtain an octet. And then the terminal carbon there has 2 hydrogens. Now you could have just been given the formula for this. C1, 2, 3, H 3, 4, 5, 6, 7, N. And then you could draw a couple of different isomers. Okay, but I started with the condensed formula for an example. Oh, actually, this formula is too short. You can't draw any more isomers there. We need more carbons and hydrogens. Okay, so that's your nitrogen. With zero formal charge, we're still not including any formal charges. You definitely want to get comfortable with your carbons having 4 bonds, your nitrogen 3 bonds in a lone pair, and then your oxygens 2 bonds in 2 lone pairs, which will give you a formal charge of 0. So again, let me give you the formula instead of the condensed structure. I'm going to start just by putting 3 carbons in a line, satisfy the octet as much as I can. So notice here there are 8 hydrogens. So if I did this, 3, 4, 5, 6, 7, 8. Okay, that's correct. Oh wait, you didn't include the oxygen. So take 1 hydrogen away. Okay, make the octet of this carbon, the one that I raised the hydrogen from, satisfied by bonding it to the oxygen, because you have to include the oxygen in the formula. So there was something I was supposed to remember about oxygen when it has a formal charge of 0. Yes, 2 bonds, 2 lone pairs. So there's 1 bond, second bond, 2 lone pairs. 1, 2, 2, 4, 6, 8. There's the octet. Then put that 8th hydrogen on the oxygen. There are a couple of other isomers I could draw here. I could place the oxygen on the middle carbon. Okay, and I like to start just by drawing single bonds on my carbons and then erasing them as I need to. So there's all the hydrogens but 1, and then I'm going to put an OH here to add my oxygen in the last hydrogen. So there's another correct isomer. I don't even need to count the number of valence electrons because there's no formal charge here, and everything has an octet in a way that gives carbon and oxygen no formal charge, or formal charge of 0, if you will. There are some more isomers for this formula for sure, so go ahead and give those a try on your own. Okay, so let's get just a little bit more complicated. So what if I have C3H6O? So if you actually just ignore the oxygens on both of those formulas, you can determine the number of double bonds in the formula. Up here, 0 double bonds. Here, C3H6, that's CnH2n. Okay, so there has to be 1 double bond because that's the formula for an alkene. So maybe I start with a methyl on the end. And maybe I want to put my double bond between these 2 carbons. Okay, that means that this carbon is going to get 1 hydrogen. This carbon has to have the oxygen because I ran out of spots. Let's put it on this carbon. No formal charge, 2 bonds, 2 lone pairs. And then the last hydrogen there. So I could draw some more isomers, so let's do that. Actually, let me give you the condensed formula for this. CH3, CH, CH, OH. Okay, so again, here's the formula. Let's try to draw some more isomers. So maybe I want to put the double bond on the oxygen. That's perfectly okay. As long as the oxygen has 2 bonds and 2 lone pairs, it'll still have a formal charge of 0. So I can do this. That carbon is satisfied. Maybe this carbon gets satisfied by drawing 2 bonds to 2 hydrogens, and then 1 bond to the 3rd carbon. Okay, so I double bond the carbon and the oxygen. The oxygen, 2 bonds, 2 lone pairs, formal charge of 0. The carbon, 4 bonds, excuse me. 1, 2, 3, 4. Still formal charge of 0. It doesn't matter if you have 4 single bonds, 2 double bonds, a double bond and 2 single bonds, a triple bond and a single bond. That's still formal charge of 0 for carbon. It doesn't matter if the oxygen has 2 single bonds and 2 lone pairs, or a double bond and 2 lone pairs. It still has a formal charge of 0. Why is that? Because when we calculate formal charge, what we're looking at is the number of valence electrons that the element came into the formula with. So if we're doing oxygen, for example, so here, let me write it out. So valence electrons, and then from that, you're going to subtract the bonds to the specific atom in the molecule, and then the lone pair electrons. So not just the lone pair, you have to count both electrons. So let's say we're talking about this oxygen here, and the formal charge is going to be 6 because that is the number of valence electrons of oxygen, a group 6 element. That oxygen in that molecule has 1, 2 bonds. Okay. That oxygen has 1, 2, 3, 4 lone pair electrons. So that gives me 6 minus 2 minus 4, 0. So why do we count the number of bonds? Because the way we look at it is the oxygen doesn't have all the electrons in these bonds, in that double bond. It's sharing them with the carbon. So essentially what you're saying, it's only really owning 2 of the 4 electrons in that double bond. But when the electrons are as lone pairs, the oxygen gets full ownership of the electrons. Whoops. Okay. And so for this oxygen up here, it would be the exact same calculation. Okay, I apologize, I keep touching my keyboard here. Let me see if I can lock it. Maybe I can't. That's okay. Okay, so we've looked at examples with carbon, with nitrogen, with oxygen, and with double bonds. I can write the condensed formula for this. CH3, CH2C, there's carbon here, O. Actually, we tend to write it CHO when we have that functional group to differentiate it from this functional group. So let's talk about what happens when we have ionic bonds as well. So we're going to have an ionic bond when we have metals, right, like sodium, lithium. Make sure I'm still recording here. Okay, yes, we're still recording. I would hate to get to the end of this and find out we're not. Okay, so when you have a metal like sodium, lithium, potassium, magnesium, or when you have a polyatomic ion. Okay, like ammonium or sulfate. Okay, so let's start with sodium hydroxide. It's not an organic molecule because you don't have any carbon in there. It's an ionic compound because you have a metal and a polyatomic ion. You just need one priority or one category to be met. When we have a metal, metals are always going to have a positive charge. Sodium, group 1, always +1. So the first thing I'm going to do is break up the ions. I'm going to write this as Na plus and OH minus. Okay, remember that the charges have to be balanced. So because sodium is always +1, that means that the hydroxide needs to be -1 to balance out that +1. So here you're just showing an ionic bond. Yay! Because you wrote the cation and the anion and you put them next to each other. That's how you should show an ionic bond. I don't want to see this ever. Ugh, that's ugly. That's not an ionic bond, that's a covalent bond between a metal and an oxygen. So this is the correct way to show an ionic bond up here. Just draw the ions next to each other. Now you haven't shown as much detail as you can if you leave it like this because you're not showing the covalent bonds in the hydroxide. Okay, so showing all the bonds, you leave your sodium just hanging out near the hydroxide. Oxygen is going to be bonded to the hydrogen. Hydrogen can only form one bond. So to satisfy the octet of the oxygen, you have to put 3 lone pairs. So that oxygen can no longer have a formal charge of 0 because it is not 2 bonds and 2 lone pairs. It's going to be -1. Okay, so if we do the math there for formal charge equals the group or the number of valence electrons of that element minus the number of bonds of the atom in the molecule, which is just 1, minus the lone pair electrons, each electron, 1, 2, 3, 4, 5, 6. That's -1. So that -1 is actually on the oxygen. So here you've shown the ionic bond. You've shown the covalent bond. It's right there between the oxygen and the hydrogen. And you've shown the formal charge. So there's a lot more detail. Now I always tell students, memorize when nitrogen, oxygen, and carbon have formal charges because we just use them so much in organic chemistry. So let's make a little list. So for oxygen, count the number of bonds, lone pairs. What charge is that going to be? Okay, and then we'll draw some examples. So you make your little table. If we have 2 bonds, 2 lone pairs, 0 formal charge. Okay, so we have oxygen with 2 single bonds and 2 lone pairs, or when we have oxygen with a double bond and 2 lone pairs, they'll have a formal charge of 0. Oops. We just saw a formal charge of -1. That is 1 bond, 3 lone pairs. Remember, each bond has 2 electrons, each lone pair has 2 electrons. So you have 8 electrons total. We still have an octet. And this is for oxygen, just make it a little cheat sheet. So the formal charge there is going to be -1. We just saw that, right? There's your 1 bond, 3 lone pairs, -1. The other formal charge to remember for oxygen that's very common is +1, and that occurs when oxygen has 3 bonds and 1 lone pair. So kind of the opposite. It's going to be +1. We see that commonly with hydronium and protonated alcohols. If you forget this cheat sheet, and really it's the more you practice, the more you're going to be able to internalize this. But if you forget, remember the formula for formal charge. It's the group minus the number of bonds minus the number of lone pair electrons. And you always have your periodic table. Start at carbon, count 4, 3, 2, 1 towards the halogens for the number of bonds that give you 0 formal charge. So let's look at another example. Let's look at one with nitrogen. So let's say you have KNH2. This is potassium amide. There is an ionic bond here, and I know that because there's a metal. Okay, so I'm going to rewrite this as the cation next to the anion. Because potassium is group 1, it has to be +1. It's group 1 metal +1 charge. So that means that to balance that charge, the NH2 must be NH2 minus. So I've shown the ionic bond. Yay! So then to show the covalent bonds on the NH2 minus, the amide, I'm going to draw nitrogen bonded to each hydrogen, and then I'm going to satisfy the octet of the nitrogen with 2 lone pairs. I have to have 2 lone pairs. There's no other way to satisfy the octet because you can't have multiple bonds on hydrogen. So that's going to give me a negative charge on nitrogen. Okay, this keyboard thing is getting pretty annoying. Okay, so just how we did for oxygen, let's summarize the formal charges of nitrogen. So we already said if you have 3 bonds and LP for lone pair, 1 lone pair, the charge is going to be 0. Okay, so that's going to happen when nitrogen has lone pair, 3 single bonds, a lone pair, a double bond, and a single bond, a lone pair, and a triple bond. Put the lone pair on the side here. Okay, all of those cases we're going to have formal charge of 0 nitrogen. Like we saw here, if we have, in the example up here, if we have 2 bonds and 2 lone pairs, then we have a formal charge of -1. The math there is 5, the group number for nitrogen, minus 2, right, formal charge, 5, the group number for nitrogen, minus 2, the number of bonds in this specific nitrogen, or the specific molecule, minus the number of lone pair electrons. Each electron counts there for the lone pairs. So then I get a -1. Okay, so 2 lone pairs and 2 bonds. And I'm only going to show that example because that's commonly what we see. And then you could have nitrogen with a positive charge, in which we have 4 bonds, 0 lone pairs, so it'll give us 8 electrons, plus 1. This could be 4 single bonds, it could be a triple bond, and a single bond. That's also very common. It could also technically be 2 double bonds. Okay. So a common example of nitrogen with a positive charge is ammonium. So NH4Cl, for example. Okay, I know this is an ionic compound because I have a polyatomic ion, even though there's no metal. So I can write this as the cation and the anion. Okay, I haven't shown any of the covalent bonds, but I've shown the ionic bond. To show the covalent bonds, I can show all the bonds between nitrogen and the hydrogens. Nitrogen with 4 bonds on it, that is plus 1. So either you remember that because you've done so many practice examples, or you do 5 minus 4 minus 0. And then the chlorine, it has a negative charge because it's chlorine with 4 lone pairs. So very quickly we could summarize the halides just how we did for nitrogen, oxygen, and that was it. So the bonds, this is a short list here, and then the lone pairs, and then the charge for the halides. So the halides being chlorine, bromine or iodine, or fluorine. So commonly 1 bond, 3 lone pairs. That's going to give us a charge of 0. That's what you're used to seeing, right? When you see, for example, chlorine. And a lot of times the lone pairs are left out and just understood that they're there. Whoops. We also see 0 bonds, 4 lone pairs, for a charge of -1, just like we saw up there with ammonium chloride. 8 electrons, all from lone pairs. Notice that no matter what the formal charge is, carbon, nitrogen, oxygen, chlorine, fluorine, they always have an octet. It's just a matter of whether that formal charge is from lone pairs or is from a certain combination of bonds and lone pairs. Now carbon can also have formal charges, and that actually leads to a lot of reactivity, so it is very important. So for example, you could have this compound. I'm going to give you the condensed formula. Lithium, CH2, 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 CH3. There's a metal, therefore there's an ionic bond. Okay, so this is going to be your positive charge. My lithium is group 1, and then this part of the molecule has to have an overall charge of -1. And I haven't talked much about overall charge versus formal charge, right? The formal charge is a charge that's specific to an atom, and the overall charge is the sum of all those charges. Because we're only looking at examples in which one atom has a formal charge, they're going to be the same. Okay, so if I want to show all the bonds here, I'm going to draw this out. This carbon has 2 hydrogens, and then it's bonded to this carbon here. And then we keep moving down the formula until we get to the very end. Almost all of the carbons have an octet except for the first carbon. I don't have any more hydrogens. I cannot draw a bond between lithium and carbon like that, right? That's a covalent bond. There's actually a lone pair in the carbon. This is what we call a carbanion, because there is a formal charge of -1 on carbon. Alright, so carbon, okay, if you're gonna memorize only one, memorize the carbon, right? 4 bonds, 0 lone pairs, charge of 0. Okay, but if we have 3 bonds in 1 lone pair, the charge is actually -1. So that's a very electron-rich carbon. Some other examples that we'll see when carbon has 3 bonds and 0 lone pairs for a charge of +1. Okay, so when would be an example like that? If we had, for example, the following molecule with the condensed formula CH3, or 3 CH3s, and then an anion, let's say a chloride, to balance the charge. Okay, so if I draw out the covalent bonds of this cation, the carbon with a positive charge there is going to be bonded to 3 carbons. Each of those carbons are going to have an octet. Okay, but this carbon is electron poor. It's actually only 6 electrons, so it has a charge of +1. You can calculate that formal charge. You do the number of valence electrons of a carbon minus the bonds, 1, 2, 3, minus the lone pair, 0, +1. And then the chloride, of course, it's -1 because it has all 4 lone pairs. So when we have a carbon that has a positive charge, we call that a carbocation. A lot of the reactions that we're going to see are going to involve that carbocation. So if you have this positively charged or negatively charged carbon, those are going to be very high energy. So it's important to be able to recognize them. So that's all the standard, the elements that we see the most. Let me just briefly cover some of the elements that can that are exceptions to the octet rule. Okay, and there's really group 3. So these are octet rule exceptions. Okay, so we have group 3. For example, boron and aluminum. So the boron in BH3 doesn't have to have an octet. Boron is satisfied with 6 electrons. Okay, 6 electrons, that's correct. And this is 0 formal charge. Okay. You could calculate that. Group 3 minus 3 minus 0, so that's 0. Now, because it has 6 electrons, that makes boron willing to accept more electrons, but this is a correct line bond structure. Same with aluminum. Aluminum is right below boron in the periodic table. A common example is AlCl3. So you can have Al, 3 bonds. into my formula there. There we go. Chlorine, they don't have any charge, so you're going to put 3 lone pairs on them. Okay, we just held this boron, group 3 was correct. Aluminum is correct there. These group 3 elements can have an octet. Just because they can have fewer doesn't mean they don't. And actually that leads to a lot of their reactivity because they can gain an electron. So some common examples, sodium borhydride. You have a metal here, that means you have an ionic bond. So we can write this as the cation and the anion. Okay, now you can draw this out to show the covalent bonds on the BH4 minus. Now that boron cannot have a formal charge of 0, right, because it's different than 3 bonds. So if you do the math, you have 3, then the group number minus 1, 2, 3, 4, so it's going to be -1. So of course the overall charge, because there's only a charge on boron. And then you also, another common reagent, lithium aluminum hydride. You have a metal, so you have an ionic bond. Oh, there's an L missing there. There's your anion. The formal charge, to give you that overall charge, is going to be on aluminum. Okay. So that's group 3, boron and aluminum. Okay, so we also have sulfur and phosphorus that are important exceptions to the octet rule because they can exceed the octet rule. So let's start with sulfur. So for example, if you have the formula Na2SO4, when you have elements that can exceed the octet rule, start with the elements that don't exceed the octet. So the first thing actually is you have a metal here, right? So this is really 2 sodiums. Sodium always +1, and then an SO4. It has to be 2 minus to balance out the 2 pluses of the 2 sodiums. Okay, so there's your ionic bond. So then I'm going to focus on the anion. You can count the number of valence electrons if you like. I always like to do that when I'm using sulfur, just to double check. So sulfur is right below oxygen in the periodic table. So same number of valence electrons, 6. So you have 6 plus 4 times 6, and then you have a charge. It's a negative charge, so that's actually going to add electrons to the total. So again, this was sulfur, and then O4, 2 minus. That gives us, how many electrons is that? 32. Okay, you didn't actually need to do this. What you could do is look at the formula for the anion. Sulfur is going to be bonded to 4 oxygens. Then focus on the oxygens. How many oxygens can I draw to have a 0 formal charge? Every oxygen needs to have an octet, but they don't all have to have a formal charge. So maybe pick this oxygen, 2 bonds, 2 lone pairs. And what I'm going to do is I'm going to try to satisfy as many of the octets as I can until sulfur has 12 electrons around it. So sulfur up to 12 electrons. And for sulfur, when you can have 12 electrons, have 12 electrons. Okay, so right now I have 1, 2, 3, 4, 5, so 5 bonds, 10 electrons. So I can make 1 more oxygen have 0 formal charge if I double bond it. Okay, sulfur is now maxed out, it has 12 electrons. So to satisfy the octet of the other oxygens, they have to have 3 lone pairs. Oxygen, 1 bond, 3 lone pairs, negatively charged. Same with this oxygen. So now all the oxygens are satisfied in terms of their octet. 2 of them have formal charge of 0, 2 of them have a formal charge of -1. Sulfur has 12 electrons around it. You can count the electrons to double check, but they have to add up to 32 here. They do, because we've satisfied the octet and we have reached 12 with sulfur, which is allowed. So when you have sulfur, give it up to 12 electrons. And whenever you have a choice, draw the sulfur with 12 electrons, and then start with the other elements, right? The ones that you know what the formal charges, what the common formal charges are. So then lastly, let's look at phosphorus. So phosphorus can have 8 electrons or 10 electrons. So if you look at first pH3, right, that's analogous to NH3, right? Phosphorus is right below nitrogen in the periodic table. So 3 bonds in a lone pair will give you 0 formal charge. There's actually another way to get 0 formal charge on phosphorus, and that is when it has 10 electrons and all from bonds. So let's say you have the formula POCl3, right? So I'm going to draw a skeletal structure, just phosphorus bonded via one bond to all the other elements, because phosphorus is your central atom. I can satisfy the octet of the chlorides by putting 3 lone pairs on each. Then I look at my oxygen. What does oxygen look like when it has 0 formal charge? Oh yes, 2 bonds, 2 lone pairs. That's a correct structure. The phosphorus has 10 electrons, and that's okay. Here I had 8 electrons. That's also correct. Now the charge here on this phosphorus, if we look at that, phosphorus, like I said, is group 5 minus 1, 2, 3, 4, 5 bonds in 0 lone pairs. So that's a formal charge of 0 in both cases. You could have drawn this instead of instead of double bonds to oxygen, you could have drawn a single bond to oxygen from phosphorus. In that case, you would have to put 3 lone pairs on oxygen to satisfy its octet. When you do that, you get a formal charge of -1 on oxygen. The formula is neutral. So overall, it needs to be neutral. It's neutral because there's a positive charge on phosphorus. If you remember nitrogen with 4 bonds was positively charged. Phosphorus is below it in the periodic table, same thing. Alright, so this has been really a bit of a crash course on drawing correct line bond structures. Start by doing practice with molecules having 0 formal charge on all the atoms. Remember what carbon, nitrogen, and oxygen and the halogens commonly have for their formal charges to be 0, and then add examples in which you have metals and polyatomic ions to practice your formal charges.